Now let's meet today's speakers. Dr. Mark Turner, CEO and founder of Turner Laser Systems, a US-based provider of advanced laser solutions for precision manufacturing. He has 15 years of experience in ultrafast laser micromachining, partners with manufacturers to turn cutting-edge laser technology into reliable, scalable processes, and combines technical depth with a strong focus on collaboration to help teams solve complex challenges and bring meaningful innovations to productions. We also have Matt Price, head of the Agile Solutions Group at PI Physik Instrumente, in which the focus is on advanced motion control solutions for semiconductors, lasers, photonics, life sciences, and imaging automation applications. He's a physicist with a background in laser materials processing and characterization, and holds several pending patents on advanced motion control algorithms. Our third presenter is Jason Gorgas, VP of Marketing at ACS Motion Control, a company that specializes in high precision motion control system solutions. Working closely with customers and partners, Jason and his colleagues strive to develop a deep understanding of application requirements and market insights to shape the company's product roadmap. Hello, all. We're so thrilled to have you with us. The floor is yours.
All right, thanks, Justine, for the kind introductions. I'll jump straight into today's webinar. So Matt and Jason and I have put together this webinar with the intention here to be an educational webinar where we'll be sharing with you from the perspective of motion providers and machine builders on via hole drilling with lasers. We'll be going into a quick little introduction into the basic foundations of via hole drilling. We'll dabble a little bit into different types of laser processes and how that applies. But our main focus today is going to be about motion. So we'll set the scene with an application of 200 micron hole drilling in glass wafers. We'll also talk a little bit about how you would adjust things if you're working with different hole sizes or different pitches. And then we'll go into sort of the core components of approaching this type of application, looking at stage architecture, motion controls, and then we sort of put it all together and then show you what does this look like running processes in the lab, and how do these key components go and lead to throughput, precision, and those core concepts. And then at the end, we'll have a few sort of what we call teasers about some other technologies that you might be interested in if you're pursuing higher precision, higher accuracy, or if you're looking to enhance your throughput. So we'll jump straight into a really quick introduction to via hole drilling here. And at Turner Laser Systems, so we essentially make laser machines and laser systems. And I often say to people, this is the game that we play. Our mission is to design and deliver systems that precisely place laser pulses at the right locations at the right time to create the desired features. And this involves not only integrating the optimal laser and optics, and myself, I'm a laser guy, so I'm very focused on the laser side of things and the process side. But equally as important are the motion systems to support the laser pulse placement. And something that I wanted to sort of lead with is often motion can be thought as a way of automating processes, but they're actually a really core part of developing and building the processes, and something that needs to be considered right from the start. So if you're not worked with via holes, I'm assuming a lot of people in this audience work with via holes and packaging in a variety of different industries, but essentially they're a central component to advanced packaging across a diverse range of materials and applications. We typically work with silicon, glass, PCBs, and ceramics. Fundamentally, it involves drilling holes in your substrates, and then there's a metallization step. And there's a whole variety of different processes to achieve the hole drilling. We won't be going through an entire presentation on laser processes, but I gave kind of an example here on the bottom right, which is a laser and etching application in glass, which is commonly used, particularly in the semiconductor industry. This is having a lot of interest. But in this case, if you hear me say laser and etch, I'm talking about processing the material with a laser, creating these modified lasered features in the material. There's an etching step, and then a metallization to create the electrical interconnect. And really, what is the optimal solution is going to depend on the material you're working with, the desired hole shape, the hole size, the throughput you're looking to achieve, and also the quality requirements. But today we're going to be focusing primarily on the motion methodologies. And I feel, compared to some of the laser processes that we often talk about in the laser industry, these are a little bit less talked about. So hopefully this provides you with some useful context if you're working with via holes. Something right from the start I wanted to talk a little bit about, because it has a major impact on how you would approach motion, is whether or not you're going to be running your processes with a galvo scanner, and so galvo-based process, or a fixed optic. And a galvo scanner or galvo-based process is where we utilize a galvo scanner to direct the laser beam onto the workpiece. And what we mean by this is the laser is scanning or moving over the workpiece while the workpiece generally is stationary. And we'll talk about some more advanced methods a little bit later. And the pros of using galvo-based processes is you can have high throughput with these processes, in the sense that you can move very quickly from hole to hole. And it says high jump time is meant to say high throughput jump time. So you can very quickly move from hole to hole. But it's also process enabler. So in certain cases, we use methods like 2D trepanning. Generally, if we're using an ablative-based method to create these via holes. And trepanning is kind of shown here on the bottom, where percussion drilling is a type of drilling where your laser fires at the same pulse after pulse to drill the hole. And a trepanning drilling is where you use something like a galvo scanner to drag that laser beam in a 2D motion at a very high velocity to sort of mill out the hole. And so the galvo scanner can be more than just going from hole to hole, but also create the shape of the hole as well. One of the downsides, though, of the galvo scanners is they're generally limited to smaller numerical apertures, generally less than 0.1 NA, and the field of view is limited. In fact, there's a trade-off between numerical aperture and field of view. There's also telecentric errors with these galvo-based solutions, and what that means from a via hole drilling standpoint is your holes won't be very straight, and particularly becomes non-straight more and more as you get towards the edge of your field of view. And if you compare this to traditional fixed optics, they're not as accurate generally, because you've introduced an additional coordinate system. So there's a time and place of when you'd want to use a galvo scanner. The other type of optical configuration we'll be talking about today is using fixed optics. And when we say fixed optics, what we mean is the laser will be stationary, and we utilize a stage motion system with synchronized triggering of the laser to the motion coordinate system in order to achieve the process. And there's many different types of fixed optics configurations. Today, we're going to be talking about glass modification processes and through glass vias, in which case, this is generally the preferred method for most applications, although I say we still use galvo scanners today for doing TGVs in glass, but with an ablative method, but they're in some more niche applications. Filamentation or bezel-based techniques are the two predominant techniques people use today. If you'd like any more information about these different laser processes, please reach out, but I won't be going into the details today. It does require, however, a post-process chemical etch with HF or KOH typically, and which chemical you use might depend on the availability from a safety standpoint of what you can get into your facility, into your city. This process doesn't work with standard galvos. And whilst in theory you can drill 100,000 holes per second, in practice, the motion system is the bottleneck. And that's going to be the core focus of our talk today, because there's a lot of promise with this technology, but the motion system needs a lot of work to enable it. So some of the key requirements in terms of form factors: we work with wafers, we work with large panels, and then we work with a variety of substrates of different sizes and thicknesses, ranging from 100 micron to millimeter typically. Taper angles of sort of a degree to 5 degrees is sort of common. You can get close to zero taper if using the laser and etch method, or if you're doing ablation, you could use a 5-axis trepanning system. People sometimes use double-sided drilling for reduced taper, but that adds a lot of complexity to the motion and alignment. And then from an accuracy standpoint, generally for the smaller holes, we're seeing about 2 to 5 micron accuracy requirement. And then once you get to larger holes, 100 micron or so, you can probably live with something in the range of about 10 micron most of the time. And from a throughput standpoint, we generally see for applications in semiconductor where you've got large panels with millions of holes, the target there is to achieve thousands of holes per second, which can be very challenging. And for other applications where you have less holes, you could usually have a much lower throughput. In terms of the laser and etch methods, generally there are two ways to approach this. You can have a single pulse per hole. It's the highest throughput. Your motion is going to be essentially focused on jumping between hole to hole. And a single pulse will create that modification, but you're going to have to aggressively etch, and it's going to reduce the wafer thickness quite a lot. Another method, which we'll be presenting today, just because it made the motion a little bit more interesting to present and provide some more education, is where you use mini pulses to create the circular pattern. And whilst this does lead in a lower throughput, because now you need many more pulses to create the hole, and it also puts more demand on the circular motion, it does mean the aggressive etching can be reduced significantly, and it also means that you're going to be having less thickness reduction of the glass material. Some other core challenges: the hole shape's important. We need to get good plating and electrical performance. We need very high uniformity from hole to hole. It's going to be important for yield. As I mentioned, motion's the bottleneck for these ultra-fast laser-based processes. Acceleration and jerk is absolutely critical. I think a lot of times people talk about speed, but really it's acceleration and jerk that's going to be driving your throughput in these applications. And then if you're working with the panels and larger workpieces, you've now got additional challenges of the inertia of such a system, as well as achieving high accuracy. And you need to think about both the static accuracy as well as dynamic positioning errors, which we'll be showing and presenting in a little bit. And finally, just summarizing sort of the application that we'll be presenting a little bit later in this presentation. We're going to be doing 200 micron hole drilling in glass, and we've chosen a pitch of 2 millimeters. It's a uniform pitch. We chose this diameter and this pitch just to make a really simple baseline, and then our goal is to show you what it looks like as you use different algorithms or different stage setups. So this is a pretty simple. The lessons that we were sharing with you here will apply to smaller or non-uniform pitches or hole diameters as well. Here we're using femtosecond laser with the cell optics, and these will result in very clean, straight, and damage-free holes. Relevant if you're working in these industries: semi, medical device, telecom, defense, microfluidics. And the motion challenges here are if you have incorrect hardware controls or synchronization, you get major issues with precision, yield, and throughput. And as a little sneak preview here, but I'll pass off to my colleague Matt to speak to the stage architectures.
Thank you, Mark. Mark has touched on a lot of key themes that we consider here at PI, especially in development of ultra-fast laser-based motion systems. So what I'd like to talk specifically here in this case, what Mark has been doing related to process. Specifically in terms of motion, I want to present on the stage architecture he's using, what we consider generally in mechanics and motion subassemblies that go into these kind of advanced laser processing tools that Mark is manufacturing through Turner Laser Systems. And I want to speak to our general philosophy and what we do for these processes and the work we do related to those. So let me jump right into what we're calling stage architecture. And if we jump into stage architecture, there are some key characteristics that touch on those core concepts of ultra-fast processes and specifically what we do for those. So I'm going to be presenting here on a V417 series of linear motor stages. As Mark kind of mentioned, we need to have high dynamics, high dynamic responsiveness, and these systems and stages tend to be linear motor systems for those reasons. Now, these processes tend to happen on travel nodes. So when we make stage series for laser materials processes, we try to get suitable travel nodes to cover a wide array of different substrates and materials. This is one particular stage series that PI manufactures that was developed and adapted for laser materials processing with ultra-fast lasers especially. But PI makes a series of these kinds of products and stages all across beam delivery and substrate motion are beam directing. So for this, we also use integrated position and temperature sensors. This is critical for high dynamic processes. With linear motors, you tend to run a lot of current on high duty cycles. We want to be aware of that current and make sure that the stages don't overheat or you get repeatability issues related to heating. And of course, that goes into controls, which my colleague Jason will be touching on downstream of this part. So of course, we want high load bearing, precision ball bearing guides. In this case, we use a quad truck arrangement, so you minimize moment loads. This is important generally because bearing life is a function of loading. And by designing and having these stages, so you minimize these kinds of effects related to loading that minimize your stage performance or lifetime. These are considered carefully as a part of the stage design, and the V417 carries this careful stage design aspect. We also like to design with low CGs, wide bases, and low moving masses. Naturally, when you get moments or you get shifting masses, you want a highly rigid motion system that has minimal kind of impact from Abbey air because your CGs are placed too high. So when you look at these systems, there's kind of a secret language that's spoken through the motion systems in these kinds of applications. And these are little cues of those motion or that language. And finally, we want something that's stiff, but also lightweight. So we tend to lean into aircraft grade aluminum alloys. There's a number that we use here, but that's critical also in terms of providing highly stiff but still lightweight motion systems that have minimal deflection. You'll hear as a common theme when we talk about these kind of processes that Mark has mentioned, where you're running drilling via curvilinear kind of pathing, you're going to hear a lot about stiffness because naturally as you come around tight corners, you want high dynamic responsiveness with kind of minimal slop with high stiffness or rigidity. So specific to this, the V417 series comes in a range of travel nodes. You can see some of these design elements I've been mentioning here with kind of wide bodies with low CGs with sloped sidewalls specifically for protective features. When you have laser material processes that are ablative in nature or debris generating, we like to have sealed construction stages. I'll talk a little bit more about that, but this series specifically has been made to prevent ingress of debris, dust, or any other kind of particulates that could contaminate or otherwise harm the stage and its extended operation. So when we step through that, PI generally makes motion sub-assemblies, and this is a part of an IMAS system series where we can provide scaled solutions from an integrated XY from the base component stages with cable management for chucks and other things with service lines. Then they can be provided on standard granite platforms, or they can be provided on standard granite platforms with bridges, or they can be provided as out-of-crate complete motion sub-assemblies specific to the process. And again, I'd like to point out that we are involved in a number of laser materials and additive manufacturing processes. And this is one such system, but we have a number of architectures that we use. This one is specific to Mark's particular process that you're seeing here. So as we step through, I want to talk a little bit more about these dynamic characteristics, especially related to acceleration, jerk, and snap, the higher order time derivative of jerk. Generally, when we do this, we want smooth, accurate dynamics without variable force as we guide. For that, we tend to lean into center drive linear motor kind of architectures. And that's what you're seeing in the V417 series and other such cases where you're dealing with femtosecond or picosecond kind of laser processes. So when we want that precise trajectory following that you'll be seeing in Mark's presentation and what Jason will speak to, we want to be able to have that stiff, rigid, high dynamic structure that follows tight corners, much like we often hear in car analogies. It's quite similar here. So we also want direct position measurement at the moving platform. So in the language of what we do here on the motion subsystems, we use linear encoders with the feedback topology specifically on the load. So there's no intermediate mechanical couplings that might otherwise provide errors in the position reporting. So this is kind of the architecture, again, for these ultra-fast ablative or non-ablative processes. and what we generally go to provide the best kind of results in terms of process that get validated at partners like Turner Laser Systems. So what does that look like practically? This is showing kind of the IMAS system with the bridging structure that's carrying the focus optics. And then you see the substrate carrying XY assembly underneath it with cable management. And when we look at that, you can see the rendering here showing that cable management, the assembly, the architecture. And now you can see, what do we use? We use ironless center drive, ironless linear motors. And what does that mean in terms of the way we design and architect these systems? Well, it's important to notice to mention there are two critical factors to this, along with rigidity. One is the peak force output of the direct drive integrated motor. And so that motor in this case is a 3-phase ironless linear motor with a peak force output of 300 newtons. And we like to keep the moving mass low, but stiff. And so in this case, the V417 series has 2.8 kilograms of moving mass. So what does that mean from a peak acceleration standpoint in terms of achievable motion? That's approximately 10 G of acceleration that the stages can provide. So 10 G acceleration in this kind of case comes with trade-offs related to air and dynamic performance, but we want to have sufficient motor force and moving mass to be highly dynamic and stiff. And that's the purpose of the V417 in processes like these. So we also have to consider, though, that these stages get put into assemblies. And this is the case here in the process that Mark has been describing with the VL hole drilling. And we have to consider that carefully also in the design of the motion architecture and expected architectures based on the component level stage assemblies. And so when we look at that, we look at force in the assembly context, and what does that mean in net applied load and the resulting peak acceleration. So if we look at that, we have a mass buildup is the way that I would describe it. And in motion, we often go to a moving mass description. In some cases, there's non-moving masses and they're not relevant for the application of motor force. So in terms of this, you can see we have a carriage mass as a part of the V417 series. We have an upper axis mass that the lower axis is carrying on that carriage. And then we have an applied payload. It's not so uncommon that we carry aluminum chucks or other kind of substrates carried on vacuum chucks or holders of aluminum construction. Typically in ultra-fast laser processes, the substrates aren't terribly heavy. So in this case, let's presume kind of a typical load of 5 kilograms, chucking, applied load, etc. And we calculate that force, and you can see that the peak force in terms of the stage is still 300 newtons on the lower axis, and with the full assembly weight, we can still move about 2 G acceleration in this kind of scenario. So this is kind of to the point of purpose-driven design, that we want something that's wide, low base, low CG, low profile, but also stiff and lightweight. So when you make assemblies, you don't suffer inertial effects when you're trying to run tight corners. So this is all on the thoughtful design of the way that this works. And the center drive does that as well, where your center drive doesn't introduce torque moments or lateral kind of moments that, again, produce negative effects in terms of path following. So now to step finally into another aspect, or the secondary aspect that's core to the design of laser materials processing stages and motion systems, we consider ingress protection. And most of these ablative processes are debris generating processes otherwise. You want to be careful to make sure that you have a sealed construction stage. You want hard covers and side seals. You want passive ingress protection through the side seals, and you want, in our case, active ingress protection with an air purging system. So this generally, the air purging system provides two benefits. It provides the benefit of you prevent debris ingress into the interior body of the stage that could be contaminating or otherwise lifetime limiting. And secondary, with an air purge, you have constant airflow so you can prevent heat buildup. So what does that look like? You can see this is what I was talking about in terms of the design. You have a low profile, in this case 70 millimeters, high stage from base to moving platform. You have slope construction and sidewalls, and you have your cable management system attached. And this is kind of the rigid, low profile design that we aim to have in these kinds of applications. And you can see an air purging line. And what does the air purging line do? First, in terms of side silling, you have that passive ingress protection. So the side sills are preventing ingress of debris or contaminants. So those side sills kind of knock it away. And the slope construction keeps it channeled away from the body of the stage. And then we have active ingress protection. You can see these blue lines kind of showing the airflow being tunneled with a positive pressure air purge tunneled into the interior body of the stage and out to the external environment. So you don't create, so you don't allow that debris to contaminate the stage internals. So when we look at these motion system subassemblies with these features that I described that you're seeing the process results from, they all get backed against high performance motion controls and drives. And that's a very important aspect to a successful process, along with the motion subassembly, stage architecture, component level design details. And so to speak to that, I'll be passing to my colleague, Jason Gorgas. Jason Gorgas.
All right, thank you, Matt. So yes, I'll be speaking today a bit more details on the motion controls or the controls system, namely the motion controller and the servo drives, the motor drives, which are driving the precision stages that Matt just explained. So I'll be talking about a few aspects of the control system that are critical for ensuring the performance and optimizing the throughput and accuracy that we present in this webinar. First, I talk a few points about profile generation. So profile generation, the process of actually commanding the motion, there are some nuances associated with that, and there are different approaches to handling profile generation. So in ACS motion controllers, the standard or default way of doing contoured profile generation, coordinated motion profiles for multi-axes, is referred to as segmented motion, which effectively consists of a path with line and arc segments. And this is common in laser processing applications, additive manufacturing applications, where you have at least two primary axes and can have additional dependent motion axes. That's commonly programmed in G-code for CNC type applications. Motion controllers often support a native language for programming this type of motion. And these motion profiles consisting of a line and arc segments, in the simple case, really just represents lines and arcs, and the controller follows the programmed velocity, acceleration, and jerk limits. But for real applications, it's important that the controller's profile generation algorithm considers some of the constraints of the system. So you can see here, for example, looking at the doing a look-ahead trajectory processing, so that the vector velocity is limited through corners is a common improvement offered for profile generation algorithm like this. Also doing geometrical processing. So even if you're trying to do generate a profile for features which have sharp corners or elements in them, inserting some amount of rounding to do smooth transitions from one direction to the next can really help with the throughput. So this is kind of one paradigm of profile generation that I'm introducing here, and is appropriate for fixed optic via hole drilling, where it's primarily just lines and arc segments or circles representing a hole. Next, I would introduce a more advanced version of contour motion profile generation that's applicable for generic profile applications, something which we at ACS call smooth path. This is a mode which generates the profile from Looks like my slide switched there. Okay. So the smooth path algorithm is, there we go. The smooth path algorithm is taking a series of points and doing an interpolation on those points. And for arbitrary features, the example shown on the slide here is taking the A from our ACS motion control logo, which has many fine features, and interpolation between those features is critical. So an advanced interpolation mode can really enhance the throughput compared with a traditional approach of doing line segments and small rounding at the intersections of those line segments. Another benefit to this type of approach is that you maintain a constant process speed throughout the entire path, which can be beneficial for a lot of applications. So this slide is showing here on the top a signals versus time plot of XY motion doing this A, in the upper plot showing it with a standard line and arc segment based approach, and in the lower plot showing smooth path interpolation based algorithm. And you can see a significant improvement in the throughput, the duration of the process, but also the lower signals, the green and the beige, represent the falling error of the axes, which are greatly minimized without any changes to the servo gains. All right, so the next slide shows a comparison that we've taken at ACS in our lab, looking at some different profile generation techniques for the same work, for the same path. And you can see that starting with the basic line and arc segment approach, and then applying corner processing or geometrical processing, or a combination of those, you can increase the accuracy, reducing effectively the position error during the process. You also reduce the time. So that XSeg, or segmented motion hybrid approach, shows here a balance of throughput and accuracy with the best accuracy or minimal following error during motion that we see from these settings. And then in the end, you see the smooth path configuration, where the throughput is reduced significantly, the profile time is reduced significantly from that interpolation approach. So that's a balanced approach that's more favoring throughput. The next slide here, I have a short video just showing the comparison of the two methods. Approach. I'll play that faster. All right, so motion profile generation is one important element. Next, I'm going to briefly move on to the control algorithms themselves. So it's one thing to command the motion in the optimal way. It's another thing to then actually follow the commanded motion in the best way with the minimal error possible. So here I present just a few advanced servo control algorithms. This one we call Servo Boost and ACS. It's an advanced proprietary control algorithm based on feedback and feed-forward control techniques, but it's doing a more sophisticated control algorithm set than PID or PID feed-forward control. And effectively, this algorithm is identifying disturbances and compensating for those in real time. And one example of classical disturbance is in a stacked motion system, the motion on one stage axis could induce some disturbance in the other axis. Could be due to non-orthogonality or some coupling between the mechanical axes. So this type of an algorithm really helps to reduce the following error, effectively increase the servo bandwidth and the disturbance rejection of the servo control loop. And on the right side of this slide, you see an example data set taken from a move and settle motion profile, where the blue represents the standard error with PID feed-forward control approach. The red represents the reduced following error by applying this servo boost advanced algorithm. The next type of algorithm I want to present here briefly is a learning-based control algorithm. So the field of learning-based control algorithms has really started to scale and grow in industrial precision motion control applications. We at ACS introduced the first commercial learning-based control algorithm a few years ago, and that's something that we continue to develop and extend its capabilities. What I show here is one version of learning-based control in which the algorithm actually learns over consecutive recipes in an application. The recipe could be something as simple as a point-to-point motion. It could be a circular motion. It could be a whole series of motions, for example, all the holes to drill in a hole drilling application. And an advantage of learning-based control over classical feedback and feed-forward based control algorithms, even advantageous over the previous algorithm I just described, is that learning-based control is non-causal. Learning-based control gives the ability to predict and compensate for disturbances in the motion system before they even occur. So it is generally true that with learning-based control algorithms, you have the potential to improve the performance at a level beyond what's achievable with feedback and feed-forward based classical feedback-based control algorithms. There are some challenges associated with learning-based control algorithms, certainly. We won't go into too much depth on that in this webinar, but it's an area of focus for ACS motion control. All right, so the next slide I'm showing here, I already spoke about profile generation, about servo control, and now I'm getting to a third key element of the control system, which is the synchronization of the motion to the laser process itself. So even if the profile generation has been optimized and the servo control has been optimized, it's still critical that the triggering of the laser or the control of the laser in synchronization to the motion is very precise. So one way of addressing that challenge is to use a dedicated module or dedicated piece of hardware to trigger the laser in full synchronization with the motion. We at ACS do offer such types of products. The one we show here is called LCI, Laser Control Interface. And as you can see on the architecture diagram on the right, it's effectively a node in an industrial Ethernet network comprised of the motion controller, the servo drives, and this node is add-on option to the control system, and it's operating in full synchronization with the motion controller that generates the profile, the servo drives that execute the control algorithms, and the laser control interface, which interfaces to the laser with digital and analog control signals. So one more slide here about that synchronization of the laser to the motion. You can see here that, for example, there's a variety of ways that you can synchronize the laser process to the motion. In the simple case, you can have pulsing based on some fixed distance along the trajectory. You can also gate the laser, turn it on and off at the beginning or end of segments. And you can even do combinations of those modes. So that's what you see on the bottom is a use case in which we not only gate the laser on and off, but when we gate the laser, we also issue a pulse command to trigger the laser during that piece of the path. Okay, so I will now hand it back over to Mark to discuss some of the process results for the use case here.
Great. Thanks, Jason. And before I jump into the results, I want to give a big thank you to Kevin Chan at the ACS Motion team, and then also Dr. George Wilkes from the Turner Laser Systems Applications team, who acquired the results that we'll be presenting next couple of slides here. So putting together all the components that Matt and Jason have just talked about, that's what we do as a machine builder and integrator. And this is the only salesy slide I have here in the presentation. But if you're interested in machines that do these types of processes with these types of motion solutions in here, we offer the TLS Kanga, which is the platform that we utilize for these types of TGV processes and other types of laser platforms. Integrates. So what we've done here today in the results you'll see is we've integrated the stages that Matt have presented and the after evaluating the dynamic requirements for this application, and then the controls that Jason has just mentioned as well, integrated that into a single system, including the advanced algorithms that Jason was talking about there as well. Software is also something that often is not talked a lot about. Software is really critical, and I will give you some examples where software makes a difference in a little bit. And for us, software does the CAD/CAM path planning and also the ability to see through a motion tracking visualizer, which is really important where you're dialing things in and getting it calibrated. So jumping into the sort of results that we achieved, bringing all these systems together, we started off using actually a different machine in our facility here called a generic stages. This essentially was a very well-tuned and calibrated micro machining system, but it was a system that was designed not for through glass vias. And I wanted to show this as a baseline, just to give you an example, is if you've built your own system, or maybe you've got a system in your facility that you're using to do these processes, and you haven't really thought about a lot of the details that Matt and Jason just presented. You know, this could be something that you might start to see in your facility. So if you look at the red curve here, you'll see how we deviate from the circular path, and that's obviously a problem for drilling holes. You're going to get weird shaped holes. And so the first thing that we did from moving from that baseline was switch over to the machine in our facility that did integrate all these components and hardware in our facility. So you see the orange, green, and blue lines here denote using that other system. And they kind of look like they're all overlapping each other. So we've sort of zoomed in here to give you an example of sort of the 2 o'clock position of the via hull. And you can see that the perfect circles, this dashed black line, generic stages were overshooting. When we moved over to the V417s that Matt was mentioning, we were able to get much closer in terms of the overall contour. But if you do zoom in, you do see a bit of an overshoot here at certain positions. And then as we applied the servo boost, we were able to get a lot better, both in terms of the throughput and in the position error. And then once we applied the learning boost algorithm that Jason was just talking about, we were able to lock on right into that circular trajectory. So this kind of gives you a nice visual representation as you apply all these different elements, how they make sort of, at least on a quantitative level, how they make improvements to the overall via hole formation. And then in terms of throughput and accuracy, this slide's got a lot of information here. So the blue bars are the process time. So you can think of this time per hole. It includes both the circular motion time as well as the jumping time from hole to hole. And then the red curve, of which the y-axis scale is on the right-hand side in a log scale, is the position error. This is the dynamic position error that we're measuring on the system. And so for this baseline system setup, we had about 250 milliseconds as our baseline throughput for each hull, and a linear dynamic position error that was just over 10 microns. And the biggest improvement that you see off this full chart was as we moved from that first machine setup to the machine setup with the V417s that Matt was talking about. And if we were using sort of a standard software approach to the way we would program it, we were able to get a pretty good improvement in the throughput from 250 down to about 200. But where the biggest improvement that you could see there is a big jump in the positional error. And you saw that in the previous slide as well, as we moved from about 10 micron down to around about a micron of dynamic position error. The next thing that we did was then we started to look a little bit more into software. And as I kind of mentioned, software is really important. So when we're programming the CAD/CAM elements and we're thinking about how do we implement certain commands and communicate with the stages, we started to imply the exeg command that Jason briefly touched on. And that gave us a big increase in the throughput that we were able to go from 200 down to below 150 milliseconds and maintain a similar dynamic position error. And then from there on, then we started to apply these more advanced algorithms that Jason was just talking about, where we started to turn on servo boost, and that was able to further increase the throughput, bringing it down to almost around about 120 milliseconds, whilst maintaining a very similar position error, or actually even a slightly better position error if you compare it to the just pure XEG algorithm that we were using. And then from there, then we started to apply learning boost. So after using the servo boost algorithm, we turned on the learning boost, and it started to learn and iterate. And you could see that at that point in time, it wasn't so much about throughput, but it was more about bringing the positional error down further and further and getting it closer and closer to that sort of perfect circle contour that you could see. So this graph here gives you a nice representation of, at the start, using maybe a tool that's not really designed for this specific application, which is where the biggest gains are, and then applying these controls algorithms really allows us to be able to hone in and get to the ideal precision and throughput. So now we're coming at the end of our time here. Just to quickly conclude, I just wanted to say that today we just looked at an extremely small subset of the world of laser via hole drilling. There's many different more materials, different processes, and every time you use a different material and different process, the way you're going to approach motion is going to be slightly different. But something that you're going to see, particularly if you're working with TGVs, is that motion is a core bottleneck to throughput and this becoming really a production grade solution. And so, you got to pay attention to selection of the stage hardware, and it's an important part going into the design of the system. The motion controls is absolutely critical, and these advanced algorithms provide huge benefits with excellent ROI. As a machine builder, these control algorithms provide excellent ROI to the application. And ultimately, besides having the right components, you need to work with someone either internally within your team or work with a partner who is going to know how to carefully integrate these components together. It does take a long time to do sort of the calibrations, the assembly, and the tuning, and they're absolutely critical to the success. So with that, we're just going to leave you with some teasers, and I'll pass back to Jason to lead us off.
All right, thanks, Mark. So first, I briefly overview XL Scan, which was mentioned previously. So as you mentioned, Mark, there are applications for which a fixed optic configuration is the best choice for the drilling application. But there are some cases in which a galvo-based process is preferable, and what we offer with the XL Scan solution, which is something which we at ACS developed in close partnership with ScanLab. This is a solution that provides the synchronization of the stage control with galvo scanning control to effectively maximize the throughput and maintain the high degree of accuracy that is provided with fixed optic configurations. So there are a variety of configuration options for an XL Scan controlled system. There are some which are suitable for TGV and through silicon via drilling applications, a wider range of laser processing applications. So that's just a brief teaser on XL Scan, which can improve the throughput of drilling applications significantly. Here's a slide which shows the architecture of that control system, comprised of ACS controller and servo drive products, ScanLab RTC6 and Excelliscan or IntelliScan scanners. These are fully synchronized between the two industrial digital networks, and is suitable for use with a wide range of precision motion stages and lasers. So that's XL Scan. The next point to highlight is that error compensation for dynamic errors in the stage, mechanical error in the stage is also critical and can significantly increase the accuracy. At ACS, we offer error mapping functions and capability built into the controller. You can do 1D, 2D, or even extend to 3D mapping use cases, and that could be 3D, 3 dimensions mechanically. That's also possible to introduce other variables into the mapping functions such as temperature. So doing a thermal compensation where the mapping actually adjusts based on the environmental temperature. All right, so with that, I will actually give it back to you, Mark, to speak a little bit more to the application of that for real world use case.
Great, and I think someone asked in the questions, what are some of the other challenges that we typically face besides the motion? You know, a big part of the challenge of getting process level accuracy, particularly for viewer holes where the hole positioning needs to be critical. One of the biggest challenges we have to do is calibrating of these systems. And something that I wanted to mention is, you know, the error map correction is absolutely critical. This is where the physical errors of the motion system are calibrated out. This means scale, skew, and what Jason was talking about there. And we see a lot of the times in industry, a lot of the times interferometry is used to do sort of one axis map for each axis, and then to combine them together into multi-axis or multiple one-axis maps. But this type of method doesn't compensate for orthogonality or any other higher order errors. Like, so if you've got straightness of one axis impacting the accuracy on the other axis. So from a machine standpoint, or if you're drilling holes on a wafer, on a paddle, that type of solution doesn't work very good. So for us, what we utilize is 2D or 3D dynamic error compensation algorithms that ACS provides. And I just wanted to share a really quick case study of what that looks like. So an uncalibrated system here on the far left, this is a histogram showing the measured errors. We use a gold standard wafer, which has sort of in the tens of nanometers range of accuracy. So we use that as our kind of gold standard. And measuring against that gold standard, we see around about plus or minus 10 micron of error. If we apply just a one-axis calibration method, meaning one-axis calibration X, one-axis calibration Y, put them together, we still see a relatively large error of plus or minus 3.6 micron. This is the error that's just coming from the stages. And then once we start to apply these two-axis or 2D dynamic error compensation methods, then we're able to get down to close to the repeatability of the stages, or about 1.5 times the repeatability of the stages. And then I'll pass off to Matt to close us out.
Thank you, Mark. So one exciting area that's existed for PI for a while with our background and expertise in piezo technology is hybrid motion systems that combine these linear motor or other electric motor kind of motion subassemblies with piezo technology and sort of piezo integrated stages or positioners. We're doing that now. One exciting area where we're doing that happens in two-photon polymerization. You can see the Statue of Liberty, where you now have processes that can resolve down to sub-100 nanometer kind of feature sizes. And then you can embed or apply piezo stages in combination with motorized stages to get really fine following and high dynamics. This is being done now, and you can see here in this graphic, kind of when we look in the context of via drilling, you can have your course positioning provided by the motorized stages, and then you can have really fine, ultra-high dynamic positioning through the piezo stages. That's what you're seeing in the lower right-hand corner, and you can see this kind of nanometer level error and trajectory following when you apply piezo stages to hybrid motion control solutions or motion solutions. So this is an exciting area where we're continuing to grow and apply. And as sort of dual experts in motorized positioning and piezo technology, it's really right along the core of what PI does. And we're looking forward to seeing more of these solutions applied in systems used at Turner and beyond. Thank you. Now I'd like to pass to Justine.
Great, thank you. That was fantastic. So now let's move into the Q&A. As I mentioned earlier, if you'd like to submit a question, just use that Q&A box on the left side rail of your screen. And we have actually quite a few already, so let's jump right in. Could you please provide some more general features of a laser for drilling, a power frequency, for example?
I can speak to this question as well. So it's a little bit of a generic sort of question here, but assuming you're working with glass, we generally work with femtosecond or picosecond lasers that's on here. I often get asked the question of how much power is needed, and it's usually actually more of a question of how much pulse energy is needed, and that will be determined by the thickness of the glass. For most common thicknesses that we work with, generally hundreds of microns is needed. You may be doing often a burst mode. So another feature you should be looking out for besides pulse energy should be bursting features. And there's a whole spectrum of research that's going on, whether or not you should be using megahertz burst or gigahertz burst. And it does vary a lot on the type of glass that you're working with. So you'll be looking for ultra-fast lasers with burst capabilities, looking at pulse energy more than power. Power comes into play when you start thinking about repetition rate. And as we talked about here, generally you're motion limited here. So very rarely are you using like 100-watt femtosecond laser to do these processes. And in reality, we're often running these lasers at a few watts to maybe tens of watts if you're doing straight lines and moving really quickly.
Okay. What is the most productive software for learning-based control?
Yes, I'll take that one. So I think there's a follow-up question saying also, in terms of software, I'm referring to the programming language. So the learning-based control algorithms are effectively one piece of the control algorithm set that we as a motion controller provider offer. So with our motion controller and servo drive products, we provide a common tool set. It's what we call application development kit. And that includes frequency-based tuning tools. And it also includes some step-by-step instructions for how to set the parameters of the control laws. Whether that's servo gains or feed forwards, or whether it's something more sophisticated as a learning-based control, it still ultimately boils down to a step-by-step process of setting some configuration parameters and then analyzing the results. And that's all done within the software package that, at least in our case, as a motion controller provider, we supply with the control system. I hope that addressed that question.
Outside of the motion system, what are your biggest challenges in making TGVs? And this question is directed to Mark.
That's a great question, since today we were focused mostly on motion. I'd say, for each unique application, the first thing we look at is the type of glass we're working with and the thickness, and that's usually going to drive what type of laser and optics. I'd say the alignment is usually a critical challenge that we work with. So identifying what are the tolerances of the placement of the hulls, what are they relative, so what are the datums that they're going to be relative to. And then a lot of the other challenges that we generally find is sometimes these materials have a coating or a layer on it as well, and that can add additional challenges to both the visual alignment steps that need to be done, as well as some of the etching steps. I also didn't talk to the etching today, and we don't do the etching process ourselves. We work with partners who do the etching process, but the etching itself is a process that needs to be sort of learned and brought into the facility as well. So you'd be working with wet etch facilities with HF or KOH generally.
Okay. Well, unfortunately, we are out of time. Any questions we weren't able to get to today will be addressed directly later via email. And don't forget to take our exit survey that will pop up as soon as we're done here. Your feedback is very valuable, and it helps us to continue creating and offering engaging content. So on behalf of Laser Focus World and Endeavor Business Media, I'd like to again thank Mark Turner, Matt Price, and Jason Gorgas for some great presentations, PI Physic Instrumente, Turner Laser Systems, and ACS Motion Control for sponsoring today's webinar, and of course, all of you too for joining us. Enjoy the rest of your day.